Welcome to the Cosmic Pie Podcast, episode 27, season 2. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
So we are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota, where winter is approaching.
Winter is definitely approaching this morning. Wow.
Yeah.
It was something else. For those that don't know, you get out here on the plains, the Great Plains, whether it's the north, the high plains around Colorado, or the southern plains, it's always windy. And today the wind was something else.
But look at today's date. Here it is, November 12th, and I have not seen a snowflake yet. Now, I didn't go looking for them, right? I just randomly, when you look outside to see what's going on, you'll see snow in the air. I haven't seen that yet this fall.
Nothing.
So that's a plus. If you don't like snow.
If you don't like snow. I mean, me, I don't care. I don't have to shovel it. So
yeah, you live in an apartment.
I live in an apartment.
Sissy.
Yeah.
Now, we do have a live chat that's running, so if you have any comments or questions that you'd like to ask us throughout the podcast, feel free to use that feature. And as a disclaimer, Robert.
Yeah, well, the opinions or anything else discussed here are those of Wayne and myself, not the university, not the department, not the College of Arts and Sciences. So we're on the hook for it.
Yeah, and we're not experts in the weather.
No, we're not.
So don't take what we say as a forecast, whether you believe us or not.
Whether you believe us or not.
See, you get that one?
I got that one. It did not zoom over my head.
Now, what we like to do, of course, is to bring up different things that we see in the news related to, even science or physics. And a lot of it's astronomy related because that's where our background is. So that's not unexpected.
Little geology in there for my case.
Yeah, in fact, I'm thinking of a great guest to try to bring on the podcast someday. And it's all sort of geology related.
Okay.
So we'll see that. And then we have potentially a special guest coming up.
Yep. We'll keep the dad on a damper.
We'll see if that works.
See about if I can really arrange it or not.
See, I'm trying to get people to come and watch live next week.
That's true. Hopefully, I'll get it arranged, and next week we'll have this special guest.
Yeah, and then if you do watch it while we broadcast live at 5 p.m. Central, you can send in your questions, and hopefully they'll get those answered.
That's what you're wanting.
Yeah, that's what I want. Feedback.
So send in questions. Oh, I get it. I see where he's going now.
Okay. Robert, ever since the space program began, which was long before I was born, but ever since the space program began, we've always had this burning desire to travel further and faster.
Yes, absolutely.
In some sense, as we go through life, we often wonder, if we could have just went a little further and a little faster in my time, I would have seen all these exotic places that I may never be able to see. At least maybe someone will see it someday, but not when we're still alive, unfortunately.
I'm remembering when the Voyagers were launched, and they people were talking about how far we'll be in another 20 years or so, and it's like, here it is, 50, and yeah.
What's the saying about trying to predict the future?
I don't know. Is there a saying about that?
Well, something about it's always hard, especially about the future or something like that, or some kind of a statement there. It's ironic, right? Irony.
Yeah.
But the thing about space travel is, in our lifetime, we're exploring the solar system. But you can always think, it wouldn't be fantastic. We could explore like Proxima Centauri.
That would be great.
And any planets that supposedly there are multiple planets going around Proxima Centauri, which for those of you who don't know is the nearest star to our sun. Mm-hmm. So it's
part of the Alpha Centauri system, isn't it? Or
it's part of the Alpha Centauri system. So there are 3 stars. Mm-hmm. One of them is very low mass, red dwarf star, as we call it.
Right.
That's Proxima Centauri. And it's on this very long orbit. It's a large distance away from the center mass of the system. Mm-hmm. And so it sort of goes way out. And it just so happens that the way out is kind of towards us. So that's what makes it the closest. If we wait a while till Proxima Centauri gets on the other side of its orbit, then it'll be the furthest of the 3 stars away from us. So we'll have to change which star is the closest. But that's millions of years from now. It won't be textbooks on that anyways. Everything will be programmed in your mind. You'll have a chip. As soon as you're born, they'll put a chip in your head, and it'll have every information that we've ever known about her in that chip already. And as you get older and more mature, then you can understand what that material is about. You see? So we don't even have to learn new things. It's
and
just
they
there.
can download more to you. And
You just
so
get
forth.
software updates once in a while, right?
Right.
So that information will be updated as we learn new things.
Now that's something that I will agree with. I think we can predict the future on that. That's coming. I don't know when, but I think that's coming.
Well, certainly implanting chips in people's heads has been
It's
talked
already
about.
happened.
I mean, I think of Elon Musk is saying stuff about that many years ago now, and others, not just him, of course.
they've done
People
it
have tried it, and
Had limited success.
yeah. So we'll see how
Yeah.
that all pans out. But imagine you don't have to do anything. So if someone can't steal your ID because they just scan your head, but then what do? Cut your head off and use that if they wanted to break in your bank account or something? I mean, they done it to fingers, and I heard of eyes. We do an eye retina scan, right?
Right.
And then they take out your eye like that. It's getting gross here, but yeah. Well, there's a way, and someone can do it illegally. They'll find some way of accessing your money and stealing all your belongings. And you name it.
I'm not a cryptographer, but it would seem to me that it doesn't matter what code you use, encryption methods, sooner or later somebody will break it.
Nor do you play one on TV.
I don't play one on TV, so I may be completely wrong there.
Puzzling, isn't it? Anyways, getting on to rocket technology, it would be great if we lived in an era not only that we explored a solar system, which we have, at least we're alive at the time we're exploring a lot of these things for the first time.
Right.
So that's nice, right? If we've been born 500 years ago, we've been exploring North America for the first time or something like that, right? Or trying.
Yeah.
We're in that time, right? Christopher Columbus, right? 1492, he sailed the blue.
So
And anyways, but to explore beyond the solar system is going to require a huge advancement in rocket technology.
Yep.
There's no doubt about it.
No.
But it doesn't stop us from trying to get there.
Right.
And getting there, would be, for example, trying to come up with a way of maybe using electric propulsion.
Right.
So this is
how does electricity propel you in space, though?
Yeah. So if you can get anything to take mass and have it released from your vehicle, then it's essentially Newton's third law. For every action, there's an equal and opposite reaction. So if you were in a rowboat in space, don't ask you how you get there. Just pretend. Follow along with my thought experiment. You're in a rowboat in space. Why would you need a rowboat in space? Like I said, don't worry about it. But in your boat is a pile of bricks.
Right.
And if you start throwing the bricks in one direction,
You'll move in the other
that'd be a good
direction.
name for a band, wouldn't it? One direction.
Bricks in the other direction?
One direction.
Oh,
Then you're propelled in the opposite direction.
right.
Right? That's Newton's third law of motion.
I mean, that's something that I got to admit and got to speak up and say people get wrong. To produce a force, you do not have to push against anything. All you have to do is eject mass in the opposite direction from which you want to go.
So if you can cause mass somehow, no matter how much mass, how little tiny it could be, individual particles, if you can eject those mass particles from your vehicle, that's going to propel you in a certain direction.
Right.
So you could set up electricity
Okay.
such that you can charge various atoms, so you strip one or more electrons from them, ionize them, so you would make it overall positively charged because you've got rid of some negative charge.
Mm-hmm.
Then you could have a sort of a grid, like think of a chicken wire,
Okay.
a wire mesh at the back end of your spacecraft. And if you charged it negatively, so as a net negative charge, then those positive ionized particles will be attracted to that negative grid.
And so they would pick up speed.
So they would accelerate towards it.
Yeah.
And some of them will collide with the chicken wire itself, but other ones will go through the opening between the wires.
Okay.
And mass will get ejected, and that will propel you in the opposite direction.
Okay, so you used electricity to throw your bricks.
Yeah, exactly.
Cool.
Now, electricity, how would that be provided? Well, solar panels if you're near a star.
Or you could use radiothermal batteries, RTBs.
The sucker's nuclear, in other
The
words.
sucker's nuclear. Does it need 1.21 gigawatts?
Yeah, that's a play on the Back to the Future movie, in case you didn't get that. But yeah, you can go nuclear and generate the electricity if you want to.
Right.
And so there are various ways you can do that. And so we've done that. We've actually have spacecraft that have, gone to several places within our own solar system using ion propulsion engines, electric rocket engines. So what you're seeing here is a paper that was just put out a few months ago, so like back in October, about advanced electric propulsion. And so it was a study done about three different case scenarios. Number one is a round trip to Jupiter. So go to Jupiter, stay for a while, then come back.
Okay.
Number two is to rendezvous with Pluto. So it's like a one-time thing. You could send a robot, unless you send the brother that you don't like the most. That would be your rendezvous to Pluto. And the other one is a journey, and we're going to explore this in more detail today, known as going to the solar gravitational lens point.
Ooh.
Now, you don't hear much about that. And to get an idea of how far away these things are, do you remember how far away Jupiter is on average?
Jupiter's is 5 AU?
5, yeah, or 10, somewhere around there.
Somewhere in
It's like 5 years to go around the solar system once, right?
Right.
So it would be a little bit more than that in AU then. So maybe it's closer to 10 AU on average.
Something like
It's
that.
something like that.
Sorry.
You can look that up.
We looked that stuff up.
But Pluto is 40 AU away on average.
Right.
This solar gravitational focal point is on the order of 550 AU away.
Oh, wow.
So I just wanted to compare
So
that to
that's
how far
about-
away Pluto is.
That's out there about Voyager. Well, no,
No.
Voyager's only 120, right?
Yeah, it's about 160.
I think we
was
looked at that last episode.
Yeah, so that was like 160 was the furthest one.
Right.
So you still have a long ways to go, and Voyager's like 47 years and counting.
Right.
We're talking about getting to the gravitational solar point in just a few years, right? So just over a decade.
But that seems a little strange because I know some of these ion engines, and they produce very low thrust, but are very efficient. So how can you get there in that short a time with the low thrust? You'd take a while to build up to any speed.
Yeah, so Jupiter, by the way, is about 5.2 AUs away.
Okay.
So, yeah. Anyways.
So we looked it up.
There's people out there like debating this. How far away is it in astronomical unit? And by the way, in case you don't know or forget, an AU is the average distance between the Earth and the Sun.
Right.
So that gives you perspective in terms of scale. So these electric propulsion engines, they work for thousands and thousands and thousands of hours, continuous.
And because you're using you're using a very small amount of fuel per second, so you don't have to have a whole lot of fuel with you, so that cuts down on your weight. So,
yeah, exactly. And so there are many different types of electric propulsion engines that one can devise. I mean, here's a list on the table that's available in the paper, and you can read it for yourself. Arc jet, and Hall effect thruster, the magnetoplasma dynamic thruster. There's a word for your friends. The gridded ion thruster. That's the grid I was telling you, they would have. Reconnecting plasmoid thruster. The lithium fueled GIT. The dual stage 4 grid DS4G electrostatic ion thruster. Okay, so there are different types, right, that engineers have come up with, right? I mean, engineers, you give them enough time, they're going to invent, almost anything, right? When you think about it, right? And that's a good thing, right? Always improving, always improving.
Right. And the other column on this table is specific impulse, which is, I could go into all the nitty gritty details, but essentially the higher that number is, the more efficient your motor is. So when we get up to those dual stage 4 grid electrostatic ion thrusters, those are ridiculously. That arc jet is, if I'm remembering my buddy James's episode and discussions with him, that 400 to 1400 second specific impulse is far better than any chemical rocket can produce. So these rockets are very efficient for the amount of fuel they use.
Yeah, and so if you look at the equations, show one equation, you lose half your audience.
Hopefully we didn't lose everybody.
That's what Stephen Hawking's publisher told him when he wrote his book. Brief History of Time.
Yeah.
He said, every equation you put in, you lose in half the readers.
Okay.
And he said, damn the torpedoes and put them in
Full speed
anyways.
ahead.
Right?
'Cause I was about to say, that book's full of equations.
So our equation today is specific impulse. And what you have is just a ratio of the exhaust speed. So think of, ions or gas particles being ejected out of the back end of the rocket, divided by the acceleration due to gravity at the surface of the Earth.
Okay.
That's what that would be. Now, when you take velocity divided by acceleration, just in terms of the units, so the velocity is meters per second. The acceleration is meters per second squared. So when you divide that that just leaves you with seconds. So specific impulse is in units of time.
Okay.
And that's where that comes from. So as Robert mentioned, the larger that value, the more efficient the rocket. So what you want is to have as large a value as possible, given the type of propulsion that you're using.
Yeah. I mean, none of these ion thrusters are going to lift you off of a planet.
No.
They just don't produce the thrust. They are, however, very efficient. So once you're outside of the gravity well of a planet, they can produce that thrust for a very long time because they're so efficient. You can build up some incredible speeds.
And that'll cut down on how long it takes to get to your target. And that's the important thing if you're humans like us. If you're not a robot, it don't really care too much, right?
Yeah.
But I mean, we don't want to wait around for 100 years for us to get to some destination. We want to get there as soon as possible.
Right.
Or it's not practical for our generation.
Yeah. And these are good for long distance. Well, that's anything in space, but Jupiter distances are greater.
When we go back to Voyager, we mentioned that was launched in 77. By 79, 2 years later, we're at Jupiter already.
Right.
We've seen some missions that get launched and it took 6 years to get to Jupiter because they do these swing-bys of Venus and Earth and Mars, and then they finally make it, right? And so that just cuts down on the power of the rocket that you need, and therefore the money.
Right.
But then you sacrifice the other end, right? You have to wait a lot longer to get to your destination.
Right.
Because you use the lower power rocket. So,
that's it.
And the trade-off is you just make the mass of your spacecraft a lot less. But then you don't have all the suite of instruments that maybe you need to do some interesting science when you get there.
And we're back to the thing of it's always a trade-off. It's always something where, if you want a high thrust, you've got to have a big rocket with a lot of fuel, and that cuts down on your payload capacity for the stuff you want to do. Or you can put a little bit of fuel with this high efficiency, and while it might take you longer to build up speed, you get out there in the end quicker with a lot more payload.
Well, I know NASA went through a period where they were building these, what they call big flagship missions, where they essentially had everything on there. It's like your wish list for Christmas or something of the instrumentation that you wanted to put on board the spacecraft.
What doesn't it have?
And they couldn't afford it. Number one, the prices go quickly to billions and billions of dollars.
Right.
And then it becomes so massive, the structure, that it's very difficult to launch it, to get it where you need to go in the right amount of time. And so they started dividing those missions into smaller, scale.
Capstone missions.
Yeah, so you get this,
something else, major missions.
So you have several missions, but then all of that's spread out. And for funding, sometimes, the climate to fund this stuff goes up and down.
Right.
Depending on the political environment. And you might have only one or two of the missions actually get launched when there should have been 4 or 5 to do all the science that the original big, huge, spacecraft was going to do initially.
And I've just got I sometimes just have to wonder how much more it actually costs to do it piecemeal like that than it would just to do the big mission.
Oh, wasn't Dan Golden, NASA administrator a few years back, faster, better, cheaper was his motto?
Right. Yes.
And that's the thing, right? It's like how best, and then it turns out, I think they made it too cheap and they had a lot of failures, if I'm not mistaken. So they went back to let's do it slower and actually double, triple, and quadruple check everything before we launch it.
Right. It's like rocket testing. You want the tests to fail. You want every one of your tests to fail, because where you don't want failure is when it really counts.
Yeah, you reach the breaking point. If you know the breaking points, then you can back away from it during the use of it. I mean, things are going to fail just because random stuff happens.
Right.
And it's unfortunate, but I mean, failures like missing Mars or either crashing. I'm not quite sure because one part of your team used metric system, the other one didn't. I mean, things like that should be unavoidable.
Things like that should be highly avoidable.
But things like that are unavoidable in the sense that something's going to happen. Because
Right.
we're humans, we make mistakes.
Right.
So
And it's physical systems. Stuff happens.
and sometimes these mistakes are unforgiving in the sense that you make the wrong one at the right time or the wrong time, if you like.
Right.
That can be game over, mission over in that
You
sense.
zigged instead of zagging.
Yeah. But anyways, so
Yep.
one of the things that this paper looked at is the 3 different scenarios where, as I mentioned, a trip to Jupiter, rendezvous with Pluto, and then to that solar gravitational lens position. And you can see on here is mission profile. So Jupiter would be a round trip. Transfer time to get there would be 2.8 years. Payload in kilograms, 12,267. And then the optimum specific impulse that you need, around 34,000. And if you notice the slide before that, those are consistent with those electric propulsion systems that can deliver that.
Okay.
For Pluto, you're looking at a time to get there. So you're not talking about a round trip time, just the time to get there, just over 4 years.
Well, that beats New Horizons time by a long shot.
Yeah, I think New Horizons, 6 years or something?
Like that.
6 or 7 years.
7 years.
And it had a small payload just because it wanted to get there fast.
Fast, yeah.
So I know it arrived in summer of 2015. So I think it was on the order. I had to look that up again, right? Exactly when that was. There's so much stuff to keep track of all this rocket launches that go on nowadays.
Right.
You have the photographic memory to remember everything. But anyway, so going to Pluto gets you there with a lot less payload, of course, 7,560. But you're using a specific impulse around 38,000, so not much different from the trip to Jupiter. Just that you're getting there a relatively short period of time, just over 4 years, so your payload is going to be lighter. So it matters, can you get by with, 7,560 kilograms? Can you? And this is all based, by the way, on using a Block 2 SLS spacecraft, the Orion spacecraft, but the Block 2 version, the one that is human rated essentially.
Oh, okay.
So you can send that up. Just don't carry too many groceries that weigh a lot with you or something, right?
I mean, that's 7,500 kilograms. That's still like around 8 tons
Yeah.
of payload.
Yeah, it's still a lot. I mean, don't bring up canned goods. Just put your food in plastic bags or something.
Right.
Something, that's the weight consideration, right? You have to really worry about that. Plus, you got to bring up oxygen and water and all the other stuff that you need to survive.
Yep. Well, that's if this was a manned mission.
Yeah, that's what I'm talking about. I'm thinking about, because it's Orion Block 2 spacecraft.
All right.
So it's
thinking
manned.
7,000 kilograms of
Yeah.
just scientific instruments, and holy cow, yeah, that's a mission.
Yeah, for sure. Now, the other one, of course, would be the one going to the solar gravitational lens point. So getting 550 AU away from the sun. So the time it would take to get there, 13 years, not bad.
Not bad at all.
That's reasonable. That's doable. That's within our lifetime. We could easily do that and get the results back from the mission and then fly another one if you wanted to.
Right.
So it's not bad. Payload mass, so 17,933. And the optimum specific impulse you need is on the order of 76,000.
That's a little outside the realm they were.
Well, if you
talking
go
about.
go back a slide, you can look at the various specific impulse for the.
Okay.
So notice the last one there. You're up to 150,000 seconds. So that's doable with that technology. So there's nothing that's out of the range of what's possible if we throw the money
If we throw the money
into
at it
the
to
development and
perfect
doing the RNA. Perfect the systems.
perfect the systems. So yeah.
So
I'm
they
all about
will
that.
work, right? So now, what's this solar gravitational lens business? Why would you go 550 AU away from the sun? Well, it's like a lens. You think of a lens like in a refracting telescope, right? The objective lens. And if you take a lens and you hold it in front of you, you look through it, things look out of focus. But if you back away from it, if you change the distance from the lens to what you're looking at, you can get it so that things become in focus. You've played around with lenses. That's the case.
Absolutely.
So you can reach the focal point of the lens itself. Now, of course, your eyeball has a lens, so that acts like the eyepiece. That's why you can get things in focus. But you have to adjust things so you're essentially at the focal point. Now, we know that, and this has been shown, of course, way back in 1919, when people photographed the total solar eclipse, and the goal was to try to measure the positioning of stars in the vicinity of the sun and see if it would the deflection of where the stars would be if the sun wasn't there compared to what they were during the solar eclipse, as a way of seeing if that's consistent with the general theory of relativity.
Right.
So light, when it's coming from stars, if it passes near the edge of the sun, that space around the sun, because of the presence of the sun itself, is curved. It's warped. And so light always follows the shortest path through space, whether that path happens to be flat or it's curved. It follows a geodesic, as we would say in general relativity. So when the light passes near the vicinity of the sun, because space itself is not flat, because of the existence or the presence of the sun, then light follows the straightest path it can, which is actually curved.
Right.
So light then can be deflected from where it would normally be if there was no sun in the way, and then the space essentially between us and that star would be flat, where light would come in on a straight line, the rays of light, the beams of light. And because of that altering in the path due to the presence of the sun, then star positions will be deflected slightly. It's a small effect. Will be deflected from where they would be if the sun wasn't there. And that deflection can be calculated from general relativity, and then you can compare the theoretical values to what you actually observed, observationally.
And that was done, and that was one of the first confirmations of general relativity.
In fact, that was done way back in August there, that eclipse that you were talking about, not the one back in April recently, but the one before in 2017, if I remember right.
People redid the experiment.
Redid that experiment. Of course, we have better cameras, better optical systems that are available to us today, and it's a lot cheaper, if you like, to do that experiment, to get the result that showed, yes, the deflection of the apparent position of the stars near the edge of the sun is consistent with the general theory of relativity.
Right.
And why you want to do it during a total solar eclipse, of course, if you point the telescope at the sun when it's not covered by the moon, then you're in big trouble.
So anyway, so this slide is basically showing where that 550 AU focal point is. That's where the rays coming from infinity, so they'd be parallel, are focused due to the curving of space-time around the sun. So if we go out 550 AU, we're using the sun as a great big gigantic lens.
Exactly.
And from that, I'm looking at this and thinking they've hypothesized that they could actually get some fairly decent images of exoplanets with it.
Well, the first thing you think of is when you look at the sort of the cartoon that you see there in the upper left, that shows the position of a star with an exoplanet, so a planet in orbit around that star, and using the sun. So the focal point we're looking at is on the right-hand side, distance of 550 AU from the sun. So if you send out a spacecraft to that position and then look then towards the sun, you can have a blocking, a occulting disk, right? A coronagraph. Yeah, you block the sunlight so then you can see things near the sun itself. Then you get this increase, number one, in the amplitude of the brightness. So that's in that table that's in the lower right. So you're talking about amplitude changes, an increase in the amplitude of the order of 10 to the 11, 1 followed by 11 zeros.
Holy cow. Wow.
It's amazing. So this is, now of course it depends on the wavelength you're looking at. So this is the value you get at 1 micron. So that's in the infrared.
So that's infrared.
Infrared. But still, that means very faint things are all of a sudden you're going to increase its brightness by this factor of 10 to the 11. That's amazing.
That's, yeah.
So things that normally would be unobservable completely and now all of a sudden become observable.
Right.
The other interesting thing is resolution, angular resolution. So you'd be able to see at 10 to the minus 10 arc seconds resolution.
And that's what happens when you have a big lens.
Yeah, exactly.
With a long focal length.
That's why we use telescopes,
Right.
like think of just refracting telescopes to keep the comparison, close to what we're actually doing here.
Yeah.
And the other thing, so you wonder, well, what does that give you? Well, you can actually resolve, this is the bottom line there in that box, you can actually resolve, that is, see not just a point of light, but actually notice it's an extended source, right, of an Earth-sized planet up to a distance of 98 light years.
You want to talk about being able to potentially find if we have neighbors in the backyard, that's going to do it.
Now, what does that mean? Well, the top right, the upper right, you see two objects, two planets. One is the Earth on the far right. The other one is what the Earth would look like using this technique if it were in orbit around Proxima Centauri,
So
the nearest
4.2
star to our
light
sun.
years away.
Yeah, just over
That's
4 light years away. That's what you would
impressive.
see. That's a 1024 by 1024 pixel image.
Wow. I'm on board. When do we launch this?
Well, how much would it cost to build a telescope
That could do
that would
that?
have this sort of ability?
Let's see.
And compare it to the cost of building a spacecraft using this advanced propulsion that can get out there in just over 10 years, so we don't have to wait around so long.
I'm gonna go on the rocket. I mean, I know what the ESA is, or the European Union is spending on their 30-meter telescope, and a 30-meter telescope will not do this.
No, definitely
Not even close.
Not even close. And the other thing is, looking at the diagram in the upper left, you think that you're only looking in one direction, but remember, you can go all the way around that,
Right.
right? And follow that distance, that orbit essentially, that has a semi-major axis of 550 AU and go all different places in the orbit, both up and down and back and forth. So you have like 2 degrees of freedom, and that allows you to cover the whole sky eventually. To look in all different directions.
Your
Eventually.
orbit times at that distance are going to be on the order of tens of thousands of years.
Well, then if you can get your manufacturing process down so it's extremely cheap.
Oh, you mean put several of them?
Yeah.
Out there. Yeah, I like
Yeah.
that idea.
Yeah,
I'll go along with
exactly.
that.
So,
Yeah. So,
but yet, so this is a great advantage. So there's a big push to do this. So if you look at the mass breakdown, you're looking at a launch. So this again, SLS Block 2 launch, total launch mass 45,000 kilograms.
Okay.
Okay, your payload would take up about close to 40% of it. So 17,933 would be the payload. The electric power system would be on the order about 17.6% of the total mass. The propellant, right, would be on the order of 22.6%. And then the actual structure of the rocket itself would take up about 20% of the mass.
Yeah,
of the
but
system.
9,000 kilograms, that's nothing to sneeze at. That's a lot of mass for doing science with.
Yes, so the payload itself is about 18,000 kilograms. So payload is 18,000.
Yeah.
You have to play with. So that's a lot.
That's a lot.
So you can definitely have a telescope system out there. You send it up unmanned, of course, right? But yeah, so
And
that's definitely doable.
And how long were they? 13 years for it to get out there?
No, so the total amount of time to get out there is 13 years.
Wow.
And that assumes a specific impulse of 76,000 seconds.
Right.
What happens if, you don't want to go too fast because you got to slow down.
You got to
zip
slow
right
down to
through
park
there.
into it.
So that's the optimal
Yeah.
trade-off, right?
I got to admit, I'd probably, so that I could get out there faster, would probably put some standard chemical propellant in there. And when it got close, use that to do the braking maneuver to set it into orbit.
Yeah, so you could use like the more advanced propulsion that produce specific impulse of 150,000 seconds.
Because it's low thrust.
Yeah,
But it'll
that
get
would
you
get you
high
out there,
speed
but
and
you
get you
can't
out there.
slow down.
Right. But you can't use
Easily.
it to slow down easily.
Yeah,
So you put some chemical thrusters on there to say,
right.
and give you the high thrust at low efficiency.
Yeah,
But it'll slow you down.
yeah. So you get out there even faster.
All right.
You wouldn't be waiting 13 years. Maybe you only get out in 8 years or something.
Right. Because you wouldn't have to turn around and
Yeah.
slowly slow down.
But the advantage of being at this position is so great that we're going to do it.
Oh, yeah. I would hope so.
Eventually.
Holy cow, I would hope so. Because, yeah, in fact, I think this is showing a satellite of a constellation of
Well, it shows that
missions out
ring.
there.
It's just that it's not a single point, right?
Right.
It's a sort of like a line that goes through the focal point.
Okay.
So it's not just a single point like you'd have in a standard lens. And of course, with a standard lens, it depends on the wavelength of light where the focal point actually is anyways, right?
Right.
So it's kind of like
pick-
that in this case.
Pick
right?
your poison. And
Yeah.
I think I agree with the 1 micron choice because that's right there. That infrared wavelength will do a lot of good at seeing exoplanets, but also a lot of other things too.
Yeah, and you could have a cluster of craft
Cluster of
out
them.
there. Mm-hmm. In fact, a spacecraft that puts out stuff, you could have on board multiple payloads that get released at some point.
Right.
And they set up station in their own way, right? They have their own onboard thrusters.
Absolutely.
So you do station keeping, independently like that. Anyways, this is something to be done. And think of advanced civilization somewhere else.
Right.
And they could take advantage of this. Mm-hmm. So within 98 light years, that means if there's an advanced civilization
Right.
within 98 light years and they're orbiting a star like our own sun, they could look back at the Earth and see that, they could see it was they'd see it as an extended source.
Right.
And be able to make out land features and things like that on the planet, right?
That's crazy. Wow. I don't know how I feel about that.
That's
But
interesting.
I'm one of those that hypothesize that incoming intelligent races won't be exactly peaceful. But that's me.
Well,
That's speculation for another
what
time.
I would say is just take advantage of what nature provides us.
Absolutely. We dang sure should be doing that.
Yeah.
All right.
Now, the other thing that's been in the news is something we haven't really talked about in the past, so it's kind of a new subject for us. And this is the subject of what's called fast radial bursts. You remember hearing about these, Robert?
I remember hearing about them, but I've got to admit that nothing ever pinged hard enough that I've actually looked into them. So I know the term, I know a general idea about what they are, but I don't know what causes them or anything else.
There's a funny story, and I don't know if I have it exactly right in detail.
Okay.
So bear with me. Mm-hmm. And the thing was, there were all of a sudden a burst of radio waves that was picked up by people operating radio telescopes.
Right.
So over a very short duration, all of a sudden there was this huge burst of radio signal. And people were wondering where it was coming from. And what they discovered was that they were recording this at about the same time people were having lunch. Now, can you think of any reason why there'd be that correlation?
What was the year?
That was just a few years ago, I think.
Okay, well,
maybe
then that
20
was the
years ago.
Microwave ovens coming on.
Yes. So what they were actually doing is when some of the scientists started going for their lunch break, and they could each take their turn, right? Not all go
Right.
at the same time, right? Other ones are staying behind watching the radio telescope, monitoring the incoming signals, or whatever their observations they're making. The other person goes off to a room somewhere, puts his food in puts the food in the microwave oven, starts cooking it. And what's one of the things you do when you're in a little bit of a rush and you want to eat your food?
I'm not sure.
You don't wait until the microwave timer goes off.
Oh, right.
You pop open the door, and that's what was happening. Was the people that popped open the door before the microwave timer went off, you actually are emitting a little bit of microwaves for a short period of time when you pop open that door, just randomly open it up. And those microwaves were being detected in the side lobes of the radio telescope.
I can believe that because most microwaves nowadays are running at about 1,000 watts when you consider that the brightest stars are on the order of 10 to the minus 11 watt.
Yeah, and you got very sensitive detectors on these radio telescopes. They were picking up these bursts of microwaves. That's in the right range of wavelengths to be
And do
detected.
keep in mind, folks, it does not have to be, when you're doing radio astronomy, you don't have to be working at night.
Yes, exactly.
So,
Yes, exactly right. You could do it depending on where your object is that you're observing. You can look at it in the daytime because there's the sky to a radio telescope is black, except
black.
looking directly at the sun. It's a radio source, so you
or
don't want to do that.
Jupiter or Saturn.
But you stay away from them. Or if there's a lightning storm nearby,
Yeah.
electrical discharge can saturate your detector and cause damage. But other than that, you can look day or night. There is no day and night to a radio photon
There
in
you
that
go.
sense. And so, but what they just so people speculate that these bursts of radio waves then were these microwave ovens, but they discovered that some of these bursts could not be explainable by the microwave oven. They were still detecting them. Okay, there's still stuff out there. And these ultimately, like I said, I'm trying to see if I remember the story, how it goes here correctly or not. And so these certain class of these bursts became known as these fast radial bursts.
Okay.
So the sudden release of radio waves, radio photons, over a duration of about a millisecond, right, a thousandth of a second or so. So it's very, very brief. But the energy coming from them, because we started to find out where they were coming from, the actual the location
distance.
and the distance, and then you can estimate how much energy must be released at that huge distance away to be detected as the strength they were detecting here at the Earth. And some of these are so energetic, these bursts, even though they last like a thousandth of a second, they were producing as much energy what the sun emits over a span of 3 days or so.
That's a lot of energy. Wow.
That's a lot of energy. And so since this time, people have been trying to find these things. And there's a big experiment that's running in British Columbia that Canada has called the CHIME experiment. And one of its major goals was to detect these fast radial bursts to try to understand the progenitors. Where do they come? What causes them?
Right.
And what are the details? And in fact, people started finding that some of them were reoccurring fast radial bursts.
Oh, wow.
So it was a burst, and then it'd go away, and then a certain time later you get another burst from the same object.
Okay.
Which is interesting. So it couldn't have been like a supernova explosion, because that would be just once.
Right.
So why would it reoccur over and over and over and over again?
It makes me think of a nova, like T Corona Borealis.
You mean the one that
we're still waiting on?
Expected nova that's supposed to went off back in the summer?
Right, that one.
And we're still waiting?
Still waiting.
We'll soon have a year, it seems, waiting for that thing.
Right.
And it still hasn't gone off, just as an update, as we're speaking here today.
I saw snapshots of a presentation where somebody was presenting that it should happen very soon because the flight is fluctuating in such a way that it seems to precursor it. So
we'll see.
We'll see.
There's a lot of uncertainty on that.
Absolutely.
And soon means plus or minus 3 or 4 months. It's
right.
So it's all relative, as Einstein said, right?
Yeah.
Now, what this recent paper is all about. So this was just published back in earlier this month on November the 6th. Is that a lot of these fast radio bursts are actually coming from massive star-forming galaxies.
Okay, so the big boys.
Yeah, so this gives you a little bit of a hint of what's the origin of these things. It's produced from star-forming galaxies. Well, star-forming galaxies have a lot of supernovae.
Mm-hmm.
And these supernova explosions will produce a number of things like a neutron star.
Right.
Or a black hole.
Right.
But some of those neutron stars, as we discovered within the last 10 to 20 years or so, can have extreme magnetic fields. Mm-hmm. Extreme magnetic fields. In fact, we call these objects magnetars.
Magnetars.
So, So the idea is maybe some of these fast radio bursts, the ones that reoccur over and over again, for example, may be coming from these magnetars. I mean, the jury's still out, right? We're still seeing if that's the case.
So we're still looking for...
We're still looking. Now, this particular paper used observation, and this is kind of neat, taken by the DSA. Now, what is the DSA? The Deep Synodic Array. That consists of 110 dishes. You see the picture there on the left side, individual dishes that are a little over 15 feet in diameter. So we're not talking about huge things.
This is the old 90s satellite dishes.
Yeah, that's right, exactly. So we're talking about that scale. And 110 of them, you can combine the signal, an interferometer, like an array, as we call it. And you can actually, therefore, allows you to detect, faint signals in what you otherwise would get, with a single dish. And the other thing, you have the high resolution.
Right.
So, and the high resolution is important because you want to see at what location in space is these fast radio bursts going off at. Right. You don't want to say, it's somewhere over there, but what does that mean, somewhere over there?
It's like your GPS. If your GPS only gives you to a location to within half a mile, that's not terribly useful. But a few centimeters, and all of a sudden, we're in business.
Exactly. Now, these dishes it's a project undergone by Caltech. So they set this thing up in a place that historically they've done a lot of radio astronomy observations. Radio telescopes are there in Owens Valley in California. So it's one of these areas where the mountains ring around the valley and act like a natural shield for stray radio signals from getting into the telescope. So it's a great place. And plus, they have their usual restrictions, anyways, right? People are not allowed to have cell phones on and all
Right.
that.
I was about to say you got to leave your cell phones at the valley wall.
You can't open your microwave doors prematurely, things like that.
Yeah.
And car ignitions, right? You have to be careful of what time you're running. Your cars are going by, because that will cause, the spark plug will release electromagnetic radiation that can be picked up by the telescope and swamp the signal of something extremely faint that you're trying to observe.
Right.
So that's always problematic, with radio. That's why they always say, let's use the backside of the moon as a natural shield from all the stray signals that are generated by human activity on the Earth.
Put a giganormous radio telescope on the backside of the moon.
And you don't even need to land on the moon to put it there. You could have it just in orbit around the moon, and anytime it's on the backside of the moon, it can make its observations.
Yeah.
So you just need something to go in orbit, and that seems like it's reasonably cheap nowadays.
Like
so maybe that'll be done in our lifetime. Who knows?
Yep.
But anyways, the combined field of view of this system, this array, is on the order of 10 square degrees. That's nothing to sneeze at.
Yeah.
To give you an idea what that means, the moon covers about a half a degree in terms of its diameter.
Okay.
So 1 square degree, you can get 4 full moons and a postage stamp of that size. So this is 10 square degrees. So it'd be 40 full moons.
Yeah.
Right, sort of. A little bit. Now the moon is not a square, so there's some space in between. But these are approximate order of magnitude estimates. Right?
Okay. Okay.
Those kind of things that we can do, or you're supposed to learn how to do when you're in school, even, right?
Yeah,
you don't have to be a scientist. You're supposed to learn that. But anyway, and the image on the right, by the way, is part of the paper showing you the sources of the fast radial bursts. So you have an optical image then overlaid with the radio detection. And you'll find that essentially most of the candidates are these massive star-forming galaxies.
Okay.
Which is interesting from that perspective. So what is the progenitor? What produces these fast radial bursts? As I mentioned, magnetars. It's on the list. So question mark, so these are these neutron stars that are created during the core collapse of a massive star that goes supernova. And how that works. I don't know, Robert, do you want to explain why you have a neutron star left over after a core collapse supernova?
I got to admit, it was something that puzzled me for a very long time, because why didn't the star just blow up? And in essence, bottom line is the core collapses faster than the outside envelope. So it's the inside envelope that gets the shock wave, produces the shock wave that comes inward and hits that now essentially solid wall of neutrons and recoils, because the solid block of neutrons isn't going anywhere. So the energy recoils off of it and blows up, which produces the supernova. And if there's not enough mass in that core, it'll go onto a black hole, or it'll stop short of a black hole, rather. Sorry. And form these neutron stars. So
yeah, and that mass limit is about 3 solar masses.
About 3 solar masses.
So in other words, if this core of neutrons has a mass greater than about 3 solar masses, it will collapse down and form a black hole.
Right.
So the really massive stars will end their lives as these core collapse supernovae and produce black holes. In fact, there's evidence, and Tim Young here in our department actually did some work on this, where you can get a situation where a really massive star will just collapse directly into a black hole.
The shock wave won't have time enough to build up to blow up into a supernova.
Yeah. And you wonder, where does the neutrons come from to build a neutron star itself?
Well, you've got some that are in the atoms itself that were originally in the core of the star.
And those atoms are mainly what when we get to this stage?
At this stage, they're mainly iron.
Yes.
And so what happens then is gravity crunches it in, the electrons are drawn in, and I hesitate to say they combine with protons, because that can't be exactly right.
Here's the thing. These cores essentially implode.
Before,
right? And as they implode, of course, the temperature goes sky high. You're talking values on the order of 10 billion Kelvin. 10 billion Kelvin. I wish I had that in dollars,
Right?
Now, when they get that high, in terms of the temperature, you're producing a tremendous amount of very energetic, very short wavelength gamma rays.
Okay, that's what
And the
happens.
gamma rays photodisintegrate the iron atoms.
E equals MC squared, folks.
And they break them apart and turn into individual neutrons and protons and electrons.
Right.
And I like this story because when you think of an atom like helium,
Right.
can't use hydrogen because we're talking about neutrons. And the most common form of hydrogen doesn't have any neutrons. Has
right.
one proton in its center. Now, when we talk about helium, we have 2 protons and 2 neutrons.
Right.
And that atom is perfectly stable. And to balance the charge, of course, it has 2 electrons normally on
Right.
the outside of the nucleus of the atom. And so the neutrons that are inside the helium atom are perfectly stable. But neutron is interesting because if you take magic tweezers and you pluck that neutron out of the nucleus of the helium atom and just set it somewhere by itself and watch it,
Neutrons are not stable.
are not stable. They will decay. So roughly in about 15 minutes, that neutron is gone.
Right.
And the decay product, what it turns into is a proton,
And an electron.
an electron,
And some muons.
an anti-electron neutrino.
Got it.
Very
Okay.
fancy,
Yeah.
right? So it changed into these 3 products. For now, we're just going to concentrate on the proton and electron.
Okay.
And since it produces electron, remember the old term for electrons? They were known as what particles? you remember
Compton
that?
rays?
No. Starts with a B.
No, I don't.
Think of radioactivity.
Oh, beta ray.
Beta rays,
decay.
right?
Yeah.
So that's beta decay,
Right.
right? When the neutron is breaking down and forming electrons as well as
Right.
beta decay. Well, you can get the inverse of that, inverse beta decay,
K
under
capture.
the extreme conditions inside of this imploding core and these high mass stars. The protons and electron will join together to form neutrons.
And they'll give off an electron
Right.
neutrino?
Yes, it's yeah. So the thing is, and it's like chemistry, right? When and a reaction goes a certain way,
Right.
because it's favorable under the condition in which it happens.
Okay.
But under a different condition or an environment that's more extreme somehow, the reaction can be made to go the other way. And that's the kind of thing that's happening here. Normally, right, in the everyday condition that we're used to in our environment, the neutron will decay. But under these extreme conditions you find in the center of these massive objects, you actually build up the neutron from the protons and electron. Well, there's already neutrons there because you broke apart the iron atoms.
Right.
So you build up essentially the abundance of neutrons in these objects. And neutrons in this imploding core are jammed side by side. And these particles, like electrons, are known as fermions. Enrico Fermi,
Right.
right, named after him. And fermions, in a way to think about it, is that they can't be in the same quantum state, as you would say.
Right.
A wrong way of thinking about it, but an easier way of thinking about it. It's like putting marbles in a container, and each marble is a neutron. And if you have a certain container with a certain volume, there's only a finite number of marbles you can put in there.
Right.
You get to the point where if you try to put in that last marble, it just won't fit. And if you jammed it in, you may break the wall of the container, like if it's
Right.
made of glass or something. So you can never get any more neutrons.
Or if the container is strong enough, you will start breaking marbles.
Right. And so so in this case, the neutrons cannot be broken apart unless, of course, the mass exceeds the 3 solar masses.
Okay.
So the ideal here then is that these neutrons are jammed side by side and they resist further collapse. That's the neutron degeneracy pressure, or neutron pressure for
Right.
short.
And the container is gravity, the gravity well it's in.
Yeah, and so that's why that core is extremely stiff. And
Okay.
all that material rains in from the outside, not knowing what's going on in the very center of these objects. And you get this rebound effect, which creates the shock wave, which is aided by neutrinos and other things. There's lots of energy. It's a high temperature environment. And that blows out all of that material out into space as these core collapse supernovae.
There you go. Yeah.
But what remains
is a neutron.
is this highly condensed object, this neutron star. Now, along with it, we know that most things have a magnetic field. Not everything. The Earth has a magnetic field.
Yep.
Our galaxy even has a magnetic field. Most stars have a magnetic field associated with them. So when these objects collapse and ultimately form these neutron stars, one of the things that can occur is you have a very strong magnetic field. Now, under processes that I don't think we know the details of, is when these neutron stars form. they can have extreme magnetic fields, very, very high magnetic field strengths. These are the magnetars. And so, and the interaction, like I said, the detail of the physics has not worked out at all. The burst of these radio waves are coming from these highly energetic, very exotic type of environments.
Okay.
Now, like I said, there's a lot of work that needs to be done here, but there is this relationship between the magnetars, these fast radio bursts, and that leads in naturally to the fact that these things are tied into massive star-forming galaxies. If you have a galaxy that's forming lots of stars, along with that are going to be these high-mass stars that only live a few million years and go supernova, creating neutron stars, and some small fraction of those neutron stars, I don't think we even know the fraction yet, turn into these magnetars that could be responsible, some
For the
additional
FRBs.
fraction of them, to give rise to these fast radio bursts.
Works for me. I mean, yeah, the question then becomes, how do we figure out what's going on? Because this isn't exactly something you recreate in a lab.
No, definitely. In fact, it's related to like the pulsar phenomena.
Right.
So in 1967, when pulsars were first discovered, at first when they thought it was, well, they jokingly thought it was signals coming from some advanced intelligence.
Right.
Because the time between flashes was so regular,
And
right? It didn't vary that at all, that they could really measure properly with the timepieces they had back in the mid-60s.
Right.
And that's just when the atomic clocks are coming along and becoming, if you like, made more precise and better. And there's been lots of developments since the 60s of keeping time, as we know. It becomes more and more precise and accurate. And so that model, the pulsar, there's a lot of details there. And the thing is, anytime you come up with a model to try to explain these kind of stuff, it doesn't mean that every single object you find
is one of them.
is going to match what your model does, right? You could study 3, because that's all that was found, and your model explains all 3 of them. But by the time you collect 1,000 of them, you find a handful that's totally different than what you'd expect.
There you go.
And that's kind of what these magnetars were like. Nobody knew that they existed until you started finding things like gamma ray bursts and of these nature.
Right.
And then we
Fast radio bursts, gamma ray bursts.
yeah,
things
all,
that.
like these things seem this general connection, this general topic of these things, ultimately all tied into these magnetars. Now,
Okay.
why do you have certain magnetars that are responsible for fast radio bursts when others aren't, presumably? How does a neutron star even become a magnetar? Why do we have
Right.
the extreme magnetic fields? We don't know 100% for sure.
Right.
People are working on this actively today. Lots of researchers are interested in this topic. But it's a really, detailed physics that things need to be worked out. And as you said, these environments are so extreme, it's hard to try to reproduce anything like this in a laboratory.
Yeah. I can't see of any way that we could reproduce this.
Yeah, you take your known laws of physics and put it in your modeling, your simulation, computer simulations, to see if you can reproduce some of the properties that these objects have.
But
There's 2 things you really want to do. Observe it to death,
right.
with any different way you can think of, every way possible, to get as much information from the objects themselves. And the other is use the most sophisticated modeling, magneto-hydrodynamics type of... Now, what does that mean? Well, googly flux capacitors, whatever you can think of. Any detailed interaction of electromagnetism, right?
Right.
Interaction of charged particles in these extreme magnetic field-like environments. Hopefully you got the physics right, or at least most of it, and see if the modeling even comes close to matching the observations.
And that's some of the problems. These environments are so extreme, we're not sure we have the physics right. This is not physics that you're going to go out and experience anywhere in your backyard, So,
Now, if you want to maybe puzzle through these fast radio bursts to ultimately, come up with a perfect model that describes all of the details, then you need to educate yourself, Robert.
absolutely.
And what's one good way of educating yourself?
Read encyclopedia. No, come to the University of North Dakota. And we've got plenty of programs that you can join in either online or on campus. If you come by on campus, you can always come by and see Wayne and I. We'll be happy to talk and discuss these things with you. But otherwise, yeah, join us. We got, as the slide shows, 120 plus online degree programs. So you can get your education sitting in your pajamas in your own home.
And even if you don't want to develop models of magnetars, come in and get a degree. Shout out to the English department.
Absolutely.
Get a degree in English, learn how to write, and write about these things.
Absolutely.
To make sure others are aware such a things exist.
Or keep us from making ourselves look foolish, because you've helped us edit these things. So yes, definitely consider that as well.
Well, we can always use science writers and editors.
Absolutely.
We need them for
We
sure.
need them.
Now, Robert, our next podcast will be a week from today. That's on November the 19th. And we always leave everybody with a quote at the end of it all.
Right?
Today's quote, fittingly, is about radio astronomy.
All right.
In
You
fact-
usually are good about picking good quotes.
In
so.
fact, it is from Carl Jansky, the father of radio astronomy, who discovered radio waves coming from beyond the Earth back in the 1930s.
Okay.
So this is an excerpt, actually, from an article that was published in 1933.
Okay.
I think I was like 10 years old at the time. No, just
No,
kidding.
just kidding.
This was published
We're not
in
that old.
Popular Astronomy. If I'm that old and look like this, that's pretty good.
That'd be pretty good. Yeah.
Must be the cornflakes that I eat every day or something. It was published in Popular Astronomy, volume 41, for those who may want to look this up themselves. And it's about the discovery of radio waves beyond the solar system in 1932. So here's the excerpt. It is discovered that the coordinates given by the data are very nearly the same as those for the center of the Milky Way. The coordinates of which point are approximately right ascension, 17 hours, 30 minutes, declination, minus 30 degrees, in the Milky Way in the direction of Sagittarius, well within the limit of error of the data. And also because the records show a small hump between the main humps, you got to like that scientific description here, in certain sections of the record, so these are chart recordings from the radio telescope, just as would be expected if the Milky Way were the source of the waves. And that is exactly correct. Carl Jansky in 1932 detected the center of the Milky Way at radio frequencies.
So he detected Sagittarius A star.
Exactly, the supermassive black hole that lies at the heart of our home galaxy.
Nice. Nice.
And with that, please give us a thumbs up, subscribe if you haven't, and thank you very much for watching.
See y'all next week, folks.